All right, so we're in section 14.5, and I was going to tell you before I started, a couple weeks ago I was writing with this thing, and the tip of the stylus was really flat on one side, so I called the company and I ordered some more. They were like $8 for a package of 10. I thought, that's not bad. But then they sent me an invoice and they charged me $14 for shipping for these 10 of these little things. And I didn't understand it. So then they sent me tracking information, and I figured out why, because they scanned it in at Commerce City, and then the next place they scanned it was in Pennsylvania. So I don't think they did it on purpose, but I thought maybe that's why they.
So did you get your money back?
No, that's a standard shipping, but I just thought it was funny to
take it out of the state.
Yeah, well, it's not standard to take it out of the state, but I thought it was kind of ironic that I was upset about how much they charged me for shipping, and they ended up shipping it across the country. So they probably ended up losing money on shipping those little things with the amount of money they charged. So anyway, surface area with double integral. So we're going to look at a surface. So we have our surface that we've been talking about pretty much all chapters. Z equals f of x, y. So we want the surface area of this surface defined over some region R in the xy plane. And we're going to say for what we're doing today that Z has continuous first partials. In our region. And R is closed and bounded. So we have a closed bounded region. Let's draw a little sketch of what we're talking about, and then we'll do our development of our surface area, a double integral for surface area. So here's our coordinates, and we have our surface, our generic surface here above the XYZ plane, or sorry, above the XY plane. And we're going to divide the surface into little elements of surface. And we're going to look at this point on the corner. I'm going to call this point IJ. And if we project that, an area, we're going to call the area of this little piece delta S for surface area, delta S sub ij. And we want to sum these little pieces over our region. So if I project this little piece down into the XY plane, I get a little rectangle in the XY plane. So in the XY plane, the side of this little rectangle is going to be delta Y sub j, and this side of the rectangle is going to be delta x sub j, or x sub I. We'll call the x's i's and the y's j's. So the surface area of our surface is just going to be the sum over these small surface elements, these delta s's. And what we're going to do to come up with an expression for the surface area is we're going to look at the tangent plane, a section of the tangent plane at this point. And we're going to use the tangent plane as an approximation, a little piece of the tangent plane as an approximation for the surface at that point. and then we're going to sum those approximations over our region. So this is our starting point. This is what we're looking at. So I'm going to switch the page and we'll draw a little section of that tangent plane. So we'll expand the tangent plane. So we would have a little piece of the tangent plane above the surface there. And we're going to look at that section. So here's our magnified view of the tangent plane. At our P sub ij. So our coordinates, our axes again. So what I'm going to do is here's P sub ij, the point that we're interested in, and we're going to use vectors as the sides of a little section of the tangent plane. So I'm going to draw these vectors in going this direction. That's going to be one side of the tangent plane, and a vector that direction for the other side of the tangent plane. And we're going to call this vector A and this vector B. So we have a little portion of the tangent plane here with these vectors as the sides of that little portion of the tangent plane. And if I project P sub ij down into the xy plane, we get our point x sub I, y sub j. And the sides down in the xy plane, if I project this down, I get my little area elements in the xy plane. So this is going to be delta y sub j, and this side would be delta x sub I. So we just magnify this little piece of the tangent plane. So this little piece of the tangent plane with the vectors A and B on the side, that's going to be a parallelogram. And vectors A and B lie along two adjacent sides of the parallelogram. So we're going to find the area of this little piece of the tangent plane and sum that area as an approximation and sum that approximation over our surface. So at P sub ij, our vector A is, we can write vector A as delta x sub I hat plus the partial derivative at that point times delta x sub I in the k direction. So this tells us how far up, how much that vector A goes up in the z direction. So this is just we can think of this as the slope times the distance we travel in that direction. And B is going to be delta y sub j in the j direction. Let me make that a subscript. Plus the partial with respect to y at our point times delta y sub j k hat. So this is just a slope in the y direction times the change in y. So now we have these two vectors, representations of these two vectors that are the sides of this little parallelogram, that's the little piece of the tangent plane. How can we find the area of that little piece of the tangent plane with those two vectors? Do you remember? The magnitude of the cross product gives us the area of that parallelogram. So let's call the area of the parallelogram, let's call the area delta t I sub j is the area of the parallelogram. bounded by or defined by a vector A and vector B. So we're going to say that delta T sub ij is the magnitude of A cross B. And we're going to form this cross product, and we're going to come up with a nice way to write our surface area. So A cross B just do the cross product is, I'll write out this determinant, I hat, j hat, and k hat. Delta x of I, 0, and our partial here. And I'm going to leave the i's and j's out of my partial here. F sub x at our point times delta x sub I. And for the third vector, I have a delta j, y sub j. And our partial with respect to y times delta y sub j. So that's going to be our determinant. And when I multiply this out, I'm going to write out all my terms, and then we'll simplify. I get minus partial with respect to x times delta x sub I, delta y sub j, lots of subscripts here, y sub j in the I hat direction, minus the partial with respect to y, times delta x sub I, delta y sub j, in the j hat direction, plus delta x sub I, delta y sub j in the k hat direction.
The delta y is
Oh yes, this should be a y. This should be a y here.
why is the first
When I do the cross product, so I cross out this row and that column, I get a 0 there and a minus there. And yes?
Well, I'm supposed to do y up at the top of here, the partial derivative times delta y squared.
So if we think of this vector as a line, so starting here, so the amount that it increases, if we think of the equation of a line, y equals, so we're starting at this point, so y equals mx. So this is the slope, this is m, and this is the distance we travel. So that tells us how far up we go. So it's like saying y equals mx. The change in the height is the slope times the distance we travel in that direction. So we're thinking of it as like an equation of a line. Does that help? Okay. So we have this delta x sub I, delta y sub j term in each term of our cross product. When I simplify this, I end up with minus f sub x I minus f sub y j plus k. And what is delta x sub I, delta y sub j? What have we been calling that in the xy plane? I just factored out the delta x sub I, delta y sub j from each term. What have we been calling that? dA. That's the little, or delta A in the xy plane, delta A at that particular point. And our magnitude of our cross product, so this is the cross product, the magnitude of A cross B is this lovely radical, the square root of f sub x squared plus f sub y squared plus 1 times delta A. All of this at our particular point ij. And the total surface area is going to be the sum of this quantity over our region. and as delta A sub ij gets smaller and smaller, and we've talked about this before, we're saying that the length of the largest diagonal approaches 0. So we're going to take that sum as delta A sub ij gets smaller and smaller, and we end up with an expression for our surface area. S is the double integral over our region of this quantity, f sub x squared plus f sub y squared plus 1 square root times dA. And we call this quantity, this radical times dA, we're going to call that quantity ds. That is our surface area increment, or tiny little piece of surface area. This whole thing, this square root of this times dA is ds. That's our surface area little increment. So what does this look like? What is this similar to? This radical with the derivative squared and the like arc length, or like parametric equations. So this is very similar to the expression we end up with for arc length, or in parametric equations, the arc length and parametric equations. So what are you going to guess about these integrals? They're going to be ugly. They're often ugly. They're often ugly because we have these quantities squared and we take the radical. So often these are ugly. But this is our expression for the surface area of this function f of xy bounded by some region in the xy plane. So any questions on our development? Using that little piece of the tangent plane and then summing the areas of those little pieces of the tangent plane. All right, let's look at a couple of examples. And often the problems that we end up doing that we can do, they're a little bit contrived so that the integrals are not impossible to evaluate. All right, we want to find the surface area. And just to go back, when we say the integrals are ugly, what we're saying is that they're difficult to evaluate, not that they're aesthetically ugly. Because they when you write them out, they look kind of nice, don't they? All right. So we want to find the surface area of this surface and our boundary, our region in the xy plane. We're going to write it in set notation. xy such that x squared plus y squared is less than or equal to 9. So first off, what is this surface? It's a plane. And our region in the xy plane is a circle. So we're talking about some kind of chopped off cone shape. All right, so let's look at our region in the xy plane. Just a quick sketch. X squared plus y squared is less than or equal to 9. I'm just going to do it in the first octant. So this is 1/4 of our region. And go to 3 and 3. So what does the region suggest in terms of our choice of coordinates? Polar. So let's use polar. So we need our partial derivatives. We have a nice function. So f sub x is 2. F sub y is -3. So our surface area is going to be the integral over our region, and I'm not going to write our limits yet, of the square root of 2 squared plus 3 squared plus 1 dA equals the double integral over our region of the square root of 14 dA equals the square root of 14 times our double integral of dA. What's a double integral of dA over a region? The area of the region, right? The integral of dA is just the area. So we're taking the double integral over a region of dA, that's just the area of the region. What's the area of this region? 9 pi, right? Just the area of the circle. Our region is a circle, so we don't even have to integrate here. We don't even have to set up our integral. The region, the double integral of dA is just the area of the region. So this is equals 14 times area of R, square root of 14, yes, which is going to be 9 square root of 14 pi, because the area of the circle is 9 pi. We didn't even have to integrate. So if you can, if the problem lets you simplify your calculations or not do your problem without integrating, save yourself some work, definitely do that. All right, let's look at one more, little more complicated example, and then one more, even more complicated example. So this one, similar setup, but we have a more complicated function. Our function is 9 plus x squared minus y squared. And our region is the points x, y, such that x squared plus y squared less than or equal to 10. So similar problem, so our function's a little more complicated. So what is this region in the xy plane? Circle. So I'm just going to do a quarter of the region. And our radius is 2, so we're here. So this is going to suggest polar coordinates again. And we're looking for our surface area here. So our partial with respect to x is going to be 2x. Partial with respect to y is going to be minus 2y. So our surface area is going to be the integral, double integral. Let's just set this up now. And I'm going to say r. Normally I like to set up, and usually you're going to set up polar coordinates in r d theta. So r varies from 0 to 2. Theta varies from 0 to 2 pi. If we could do 0 to pi halves and multiply by 4, we could do it either way. And then our function, I think I need a little more room here. So we're going to have the square root of 4x squared plus 4y squared plus 1 and r dr d theta. And I know I haven't written this as in terms of polar coordinates. So how am I going to write my integrand in terms of polar coordinates? So it's going to be 4 r squared plus 1, square root of that, r dr d theta. This one's not a difficult one to evaluate because it's a u substitution. Let u equal 4r squared plus 1. The u equals 8r dr, and we have the r dr there. So this would be a u substitution, and not a difficult u substitution to evaluate. And then we end up with the integral of d theta on the outside from 0 to 2 pi, so that just gives us a factor of 2 pi in our final answer. So I'm not going to evaluate this one, but this is our setup. This one wouldn't be hard to evaluate. Any questions on that one? And every time I see, I can't help it now when I see RD theta, I think RDR. All right, last example. We want the surface area of the portion of the cone z equals 2 square root of x squared plus y squared. This is a lovely cone like we talked about in our project. That is inside the cylinder x squared plus y squared equals 4. So what is this problem asking us? How do we translate that into what we're going to work with? Well, first off, what's our function? What's our surface? The cone. What is the cylinder telling us? The cylinder's telling us our region, right? So our region, the cylinder's telling us our region in the xy plane. So if I were to draw, and this is, my sketch is not going to be beautiful here, but we have this cone, like so. And we have a cylinder that's cutting through the cone. So we're looking for the surface area of the cone that's inside the cylinder. So the cone is cut, the cylinder is cutting off the cone, so we want the surface area of that cone that's inside that cylinder. So the cylinder is telling us our region. So our region is x squared plus y squared less than or equal to 4. So in the xy plane. So this is going to look familiar. There's 2, that's a quarter of our region. So we're going to want to set this up in polar coordinates, and this is our function. So our partial with respect to x, so z sub x, what's z sub x going to be? I'll get you started. 2x. X squared plus y squared to the negative 1. And z sub y? Question? And this is symmetrical in x and y, so we just end up with 2y times x squared plus y squared to the negative 1/2. And when we take our radical, so we want to take the square root of z sub x squared plus z sub y squared plus 1. Now this doesn't look nice starting out. So we get the square root of 4x squared over the square root of x squared plus y squared plus 4y squared. Yes, thank you. The radical does go on. And plus 1. All right, anybody see what's happening here? What's going to happen? What's that? So we need to add this 1, we need a common denominator of x squared plus y squared. And it's even better than that. So let me write out this with our common denominator. It's even better than that. It's even better. 4x squared plus 4y squared plus x squared plus y squared all over x squared plus y squared equals square root of 5. So we have 5x squared plus 5y squared. Factor out the x squared, factor out the 5, the x squareds and y squareds cancel, and we end up with square root of 5. Isn't that nice? What's that? 4x squared, I'm sorry, 5x squared plus 5y squared. So we factor out the 5, and we get 5 times x squared plus y squared over x squared plus y squared, and we get the square root of 5. And then in polar coordinates, our surface area is going to be the integral from 0 to 2 pi, the integral from 0 to 2 of square root of 5 RD theta, and the square root of 5 RD theta evaluated over this is just square root of 5 times area of circle. So all we had to do was a little bit of algebra, and our integral was really easy. This thing that looked really ugly turned out to be like the toad. Give it a kiss and it turns into the prince. What's that?
It's the area of the circle is all is RDRD.
The integral, so we're integrating the entire region. Yeah, 4 pi. So this would be 4 square root of 5 times pi, or 4 pi square root of 5. So that one wasn't too bad. So yeah, Lee, if you might try it. Give your integrals a kiss and see if they turn into something beautiful. If you like. All right, homework. Yeah. Depending on the integral, it might help. I can't guarantee it.
$5,000.